Modules and Homological Algebra, Lecture 5, Generators and Relations. Let us start with this notion in relation to semigroups. We start with the notion of generators for a semigroup. Let S be a semigroup, and let X be a non-empty subset of S. Consider the intersection of all subsemigroups T of S which contain X. We denote it by X in this kind of triangular brackets. Of course, by definition, this original set X belongs to this intersection, and so this intersection is a non-empty set. Also, being the intersection of subsemigroups, this set is a subsemigroup of S. So this set is called the subsemigroup of S generated by X. For example, if you consider the additive semigroup of all positive integers and take X to be the set consisting of one element 2, then the semigroup generated by 2 is the subsemigroup of all even positive integers inside all positive integers. Now we can define the notion of a generating set. Let S be a semigroup and X a non-empty subset of S. We will say that X is a generating set for S, provided that the subsemigroup generated by X in S coincides with S. If X is a generating set for S, then the elements of X are called generators. For example, the singleton set consisting of 1 is a generating set for the semigroup of all positive integers with respect to addition. Lemma: a non-empty subset X of a semigroup S is a generating set for S if and only if each element S in S can be written as a product of elements in X. Proof: let T be the set of all elements S in S, which can be written as products of elements in X. On the one hand, T of course belongs to any subsemigroup of S containing X, because it contains X and it contains all products, and the semigroup should be closed under products. On the other hand, T is a subsemigroup of S. If we have some element which is a product of elements in S, and some other element which is a product of elements in X, we can multiply them and the product will again be a product of elements in X. Therefore, T coincides with the smallest subsemigroup of S generated by X and hence is equal to S, because X is a generating set. Next, let us talk about quotients of free semigroups. Let S be a semigroup and X a non-empty generating set of X. Consider this free semigroup f of X on X. The identity map on X gives rise to a surjective semigroup homomorphism π from this free semigroup to S. This follows directly from the free property of the free semigroup. Any map on X can be extended to a semigroup homomorphism from this free semigroup to the target semigroup. Definition: we say that a semigroup S is finitely generated if it has a finite generating set. So for example, we already mentioned that the singleton 1 generates the additive semigroup of all positive integers. So this semigroup is finitely generated. Example 2, every finite semigroup is finitely generated because we can take the whole semigroup as a generating set and it will be finite. Relations: let S be a semigroup and X a non-empty generating subset of S. As mentioned on the previous slide, we then have a surjective homomorphism from the free semigroup generated by X to S, which extends the identity map on X. Let Y be a binary relation on our free semigroup such that the minimal congruence of this semigroup which contains Y coincides with the kernel of our homomorphism π. Then, by the first isomorphism theorem, we have that the semigroup S which coincides with the image of pi, because pi is surjective, is isomorphic to the quotient of f of x by the kernel of pi. Definition: the elements of Y are called relations. And in the situation as described above, one says that the semigroup S is given by the generators X and relations Y. And this is denoted as follows. So the semigroup S is given by generators X and relations Y. So we put a vertical line between them and take them into some triangular brackets. And this is called a presentation of S. So we define S in terms of generators and defining relations. And another small definition, a semigroup S is called finitely presented if there are finite X and Y such that S is given by the generators in X and relations in Y. So we have both finitely many generators and finitely many relations. Example, so we claim that the semigroup of all positive integers with respect to addition is given by the generating set consisting of 1 and without any relations, so the empty set of relations. So we already know that the singleton 1 generates this semigroup. If you consider the free semigroup on the singleton set 1, it will have as elements all words in the alphabet 1. So we will have 1, then 1, 1, 1, 1, 1, and so on. So all finite non-empty words in this alphabet. Under our surjection map pi from this free semigroup to the additive semigroup of positive integers, the word 1, 1, 1, 1, 1, which has k letters 1, this is mapped to the integer k, which is a positive integer. Therefore, this map is bijective. So each word is mapped to an integer and different words are mapped to different integers. And hence, the kernel of pi is the equality relation. And the minimal congruence on our free semigroup generated by the empty set is, of course, the equality relation. And this implies our claim. Alternatively, we could have taken at the set of the defining relations Y any subset of the equality relation on our free semigroup f of 1. Now let us talk about all this stuff, but now for monoids. So let M be a monoid and X a subset of M. We consider the set, denoted by X in triangular brackets, which is the intersection of all submonoids of M which contain X. Again, by definition, X belongs to this set, and the set is a submonoid. It's the intersection of certain submonoids. And this set is called the submonoid of M generated by X. Please note that the set is automatically not empty, it's a submonoid, so it contains the identity element of M. So for example, if we take the monoid of all non-negative integers with respect to addition, so the identity element is 0, and the set X consisting of the integer 3, then the submonoid generated by 3 will be submonoid of all non-negative integers divisible by 3. Next, we can define the notion of a generating set. Let M be a monoid and X a subset of M. We say that X is a generating set for M, provided that the submonoid generated by X in M coincides with M. If X is a generating set for M, the elements in X are called generators. So for example, the singleton set 1 is a generating set for the monoid of all non-negative integers with respect to addition. Lemma: a non-empty subset X of a monoid M is a generating set for M if and only if, for all elements in M, we can write M as a product of elements in X. And we have the same proof as for semigroups. We denote by N the set of all elements in M which can be written as products of elements in X, and consider the union of n with the identity element. On the one hand, it belongs to any submonoid generated by M. On the other hand, it is a submonoid. And so X is a generating set if and only if n union with the identity coincides with M. Next, let us talk about quotients of free monoids. Let M be a monoid and X a generating subset of M. We can consider the free monoid f of x on the set X. Similarly as to the semigroup case, the identity map on X gives rise to a surjective monoid homomorphism π from this free monoid to M, and this is a direct consequence of the free property for f of x. Definition: we say that M is finitely generated if it has a finite generating set. So for example, as the singleton 1 generates the additive monoid of all non-negative integers, the later monoid is finitely generated. Example 2, every finite monoid is finitely generated, as we can take X to be the set of all elements in this monoid. It's finite. Now we can talk about relations. Let M be a monoid and X a generated subset of M. Let π be the corresponding surjective homomorphism from the free monoid generated by X to M. Let Y be a binary relation on f of x such that the minimal congruence on f of x containing Y coincides with the kernel of π. Then, by the first isomorphism theorem, our monoid, which is the image of π because π is surjective, is isomorphic to the quotient of f of x by the kernel of π. So in this case, the elements of Y are called relations, and we say that the monoid M is given by the generators X and relations Y. And we have the same notation as for semigroups. So M is isomorphic to the monoid generated by the generator X and given by the relations Y. So this is called the presentation of M. And the monoid is finitely presented if we have a finite presentation. There is a finite set of generators for which we have a finite set of relations. For example, the monoid of all non-negative integers with respect to addition is given by one generator, the singleton set 1, and no relations, the empty set of relations. Indeed, we already know that 1 generates this monoid, and the monoid, the free monoid generated by the singleton set 1, has as elements exactly all finite words in the alphabet 1. So we have the trivial word epsilon, the word of length 0, and then the words 1, 1, 1, 1, 1, 1, and so on. And under our surjective map π, the word 1, 1, and so on 1 with k letters is mapped to the element k in our monoid of all non-negative integers. Therefore, the map π is actually bijective. Not only it is surjective, it is also injective. And so the kernel of π is the equality relation, and the equality relation is generated by the empty set. It is the minimal congruence on π. And so we have our claim. And of course, alternatively, we could have taken as relations any subset of the equality relations on f of 1. Next, let us talk about all this in the setup of groups. Let G be a group and X a subset of G. Consider the intersection of all subgroups in G which contain X. We denote this intersection by X in these triangle brackets. Clearly, X belongs to this intersection, and this intersection is a subgroup of G. The terminology, this intersection is called the subgroup of G generated by X. For example, if we consider the group of all integers and take X to be the set consisting of the two integers 4 and 6, then the subgroup of G generated by these two elements coincides with the group of all even integers. Next, we define the notion of a generating set. Let G be a group and X a subset of G. Definition, we say that X is a generating set for G, provided that the subgroup of G generated by X coincides with G. If X is a generating set for G, then the elements of X are called generators. Example, the set consisting of two integers 2 and 3 is a generating set for the additive group of all integers. Indeed, we can write any integer in the form 3 times some integer plus 2 times some integer. Please note big difference between subgroups generated by some elements and subsemigroups generated by some elements. A subgroup generated by some set must also contain inverses of all its elements because it must be a subgroup. So the subgroup generated by 2 and 3 automatically contains -2 and -3 inside the additive group of all integers. And we have the same lemma as for semigroups and monoids. And an empty set X of a group G is a generating set for G if and only if any element in G, which is not an identity element, can be written as a product of elements in X or their inverses. This is a very important thing about the inverses. And we have the same proof. We denote by H the set of all such elements, and this set, united with the identity element, of course, belongs to any subgroup generated by X, and on the other hand, it is a subgroup. So X generates G if and only if this set coincides with G. Now we can talk about quotients of free groups. Let G be a group and X a generating subset of G. Then we have the free group f of x on X, and the identity map on X gives rise to a surjective group homomorphism from this free group to G. So this follows directly from the free property of f of x. And we say that the group G is finitely generated if it has finite generating set. So for example, the additive group of all integers is finitely generated because it's generated by a singleton set 1. And every finite group is finitely generated because we can take as generators the whole group. Next, we can discuss relations. Let G be a group and X a generating subset of G. Then we have the corresponding surjective homomorphism π from the free group on X to G. Let Y be a subset of the free group such that the minimal normal subgroup of the free group f of x, which contains Y, coincides with the kernel of P. Then, by the first isomorphism theorem, our group, which is the image of our surjective homomorphism π, is the quotient of f of x modulo the kernel of π. So the elements of our set Y are called relations, and we say in this situation that our group G is given by the generators X and relations Y. And we have a similar notation for this as for semigroups and monoids. And also a similar definition that a group is finitely presented if it has a finite set of generators for which we have a finite set of defining relations. For example, the additive group of all integers is given by the following finite presentation. We have one generator, which is the integer 1, and no relations, the empty set of relations. Indeed, we already know that the integer 1 generates the additive group of all integers, and the elements of the free group on the singleton set 1 are exactly so the empty word and then the words in the alphabet 1 and the words in the alphabet 1 inverse, which we denote by 1 overlined. So we have 1, 1 overlined, 1, 1, 1 overlined, 1 overlined, and so on. This is because we have the relations that 1, 1 overlined is the identity and 1 overlined 1 is the identity. Under our surjective map π, the word 1, 1, 1, 1, 1, and so on with k digits is mapped to the positive integer k, And the word one overlined, and so on, one overlined with scale letters is mapped to the negative integer minus k. And so our map pi is bijective. And this means that the kernel of pi is the identity subgroup. And of course, the minimal set which generates the identity subgroup is the empty set. So this implies exactly that our presentation gives the additive group of integers. Alternatively, we could have taken as our presentation, instead of the empty set, we could have taken simply the empty word in our alphabet, which is epsilon. Finally, let us talk about generators and relations for algebras. Let A be an algebra over some field K, and let X be a subset of A. Now we can consider the intersection of all subalgebras B of A which contain X. So we denote it as previously X in these triangular brackets. Of course, the original set X belongs to X, and X is also a subalgebra of A. So here, please note that we consider only unital algebras and unital subalgebras. So in particular, the subalgebra generated by X contains the unit element, so it's not empty. And so this X in triangular brackets is called the subalgebra of A generated by X. So for example, if we take the algebra of all polynomials in T, and we take as X the monomial T squared, then the subalgebra generated by T squared is the algebra of all polynomials in T squared. It's a subalgebra in the algebra of all polynomials in T. Now let's talk about generated sets. Let A be an algebra and X a subset of A. Definition, we say that X generates A, provided that the subalgebra of A generated by X coincides with A. And if X generates A, the elements of X are called generators of A. So for example, the set consisting of the polynomial X plus 2 is a generating set for the algebra of all polynomials in X. Any polynomial in X can be written as a polynomial in X plus 2. And similar lemma as to in the previous cases, a non-empty subset X of an algebra A is a generating set for A if and only if every element in A is a linear combination of the identity element and the elements of the form x1, x2, and so on xk, where xi are in X. Proof: let B be the set of all such elements, of all linear combinations of the identity and the elements which are products of the elements in X. On the one hand, B belongs to any subalgebra of A containing X. On the other hand, it is a subalgebra. And so the subalgebra is equal to A if and only if what is generated by X is equal to A. Now we can talk about quotients of free algebras. Let A be an algebra over a field K, and let X be a generating subset of A. Consider the free K algebra f of X on X. Similarly to the previous cases, the identity map on X gives rise to a surjective algebra homomorphism from this free algebra to A. We denote this homomorphism by pi, and its existence follows directly from the free property of f of X. So we say that our algebra A is finitely generated if it has a finite generating set. So for example, the algebra of all polynomials k of x is finitely generated because the singleton set consisting of x plus 2 generates this algebra. Also, every finite dimensional algebra is finitely generated. So we can take as a generating set any basis of A. In the lemma, we had linear combinations, so a basis clearly generates an algebra. And finally, we can talk about relations. Let A be a K algebra and X a generating subset of A. Then we have the surjective homomorphism pi from the free algebra on X to A. Let Y be a subset of f of X such that the minimal ideal of our free algebra f of X containing Y coincides with the kernel of pi. Then, by the first isomorphism theorem, our algebra A, which is the image of our surjective homomorphism pi, is isomorphic to the quotient of f of x by kernel of pi. And then the elements of y are called relations. And in the above situation, we say that the algebra A is given by the generators x and relations y. And we have a similar notation as in all previous cases. And we say that an algebra A is finitely presented if it has a finite generating set for which we have finitely many relations. For example, the polynomial algebra in one variable x is finitely presented. It has one generator x and no relations, the empty set of relations. To prove this, first note that x clearly generates k of x. And if you consider the free algebra on x, the elements of the free algebra on x are all linear combinations of all possible words in the alphabet x, including the empty word. And under the map pi, the word xxx and so on with k letters is mapped to the monomial x to the power k. And these monomials form a basis in our algebra, and this means that our map is bijective. So our surjective homomorphism pi is in fact bijective, and so the kernel is 0. And of course, the 0 ideal is generated by the empty set of relations. And so this implies the claim of our example. Alternatively, we could have taken as a set of relations the element 0 in our free algebra. And here comes some motivation to explain the practical applications of generators and relations. Assume that Q is an algebraic structure, which means a semigroup, monoid group, or an algebra, and Q prime is an algebraic structure of the same type. Assume that Q is given by some presentation. It has generators x and relations y. Assume that we want to solve the following problem. How to construct a homomorphism from Q to Q prime? And here is the answer. Any homomorphism f from Q to Q prime is uniquely determined by the images under f of the elements from our generating set x. And in order for this to be a homomorphism, these need to satisfy the relations which are given by the relations in y. Proof. So the collection f of x, where x is in x, defines a unique homomorphism from the free structure on x to Q prime. This is exactly the free property of f of x. If the relations in y are satisfied for these images f of x, then this homomorphism factors through the quotient of f of x by the kernel of pi exactly by the factorization lemma. So here is the main application of the factorization lemma in our theory. So for example, we saw that the additive semigroup of all positive integers is given by the presentation. It has one generator 1 and no relations. So this means that any semigroup homomorphism from this semigroup to any semigroup S is uniquely determined by choosing in the semigroup S the image for our generator 1. No relations. So this is how in practice we use generators and relations. And at the end, some problems and questions. Question 1. Prove with all details that the intersection of subsemigroups is a semigroup, provided that it is not empty. Question 2. Construct an example of a semigroup that is not finitely generated. Question 3. Find a semigroup presentation for the semigroup of all non-negative integers with respect to addition. Question 4. Find a monoid presentation for the monoid of all integers with respect to addition. And question 5. Prove that the subgroup generated by the integers 4 and 6 inside the group of all integers with respect to addition coincides with all even integers. So prove this with all details. Thank you very much and see you next time.